In yesterday class, we have discussed about thermodynamic potentials. So, in order to explain a thermodynamical state of a system, we need thermodynamic variables like pressure, volume, temperature, and entropy. But in order to explain the thermodynamic state of a system thoroughly or completely, along with the four thermodynamic variables, we need four thermodynamic potentials. Those are internal energy, enthalpy, Helmholtz function, and Gibbs function. After that, we have seen each and every thermodynamic potential clearly. What is internal energy? The total, the sum of kinetic energy and as well as potential energy is called internal energy, and that can be denoted by U. From the two laws of first and second thermodynamics, we have written another equation, that is TdS equal to du plus pdv. From that, we have written du equal to TdS minus pdv. From this equation, we have written two more equations. In a situation that if you take entropy as a constant, volume as a constant. If you take entropy as a constant, then minus P equal to dou U by dou V at S. If you take volume as a constant, then T equal to dou U by dou S at V. That means at a constant volume, the rate of change of internal energy with the entropy is equal to temperature T. Similarly, at a constant entropy, the rate of change of internal energy with volume is equal to equal to pressure. Here, negative sign indicates the work is on the system. The work is on the system. Similarly, after that, we have seen the enthalpy, total heat system. Enthalpy H can be explained with a relation H equal to U plus PV, where PV gives us the total work done. Therefore, here U is, this is a total internal energy, H equal to U plus PV. So you should have differentiated, and you have to submit the value of du, and after that you can get the value of TH, TDS plus VDP. From that, at a constant S and at constant P, you can get these two values. Similarly, after that, we have seen Helmholtz function. What is Helmholtz function? This can be defined with a relation F equal to U minus Ts. Here, U is the internal energy and T is the unavailable energy. That means, if you subtract this unavailable energy from the internal energy of the system, then you can get available energy in the system. So that is why this energy is called as Helmholtz free energy. Helmholtz free energy. If you differentiate this equation, you can get this equation. In this, if you substitute the value of du, then these both terms are cancelled out. Then you can get F equal to minus PdV minus SdT. From that, if you take V as a constant and T as a constant, then you can get these two equations. After that, we have seen Gibbs function, G. So, Gibbs function can be defined with a relation G equal to H minus Ts, where you know what is H. Here, H is an enthalpy and Ts is the unavailable energy in the system. So if you subtract this C value from the enthalpy, then you can get Gibbs function or Gibbs energy. All these thermodynamic potentials are energy functions. So again, differentiate this equation, substitute the value of dH, and these two terms will be cancelled out, and you can get dZ equal to VdP minus SdT. So from this, if you take pressure as a constant, if you take temperature as a constant, then you can get these two values. Like this, you can explain thermodynamical functions, potentials. Okay, after that, we go for Maxwell's equations. How Maxwell's equations can be derived. So, by using Maxwell's equations, one can derive any sort of equation. One can explain any sort of equation related to thermodynamics. That is the advantage of Maxwell's equations. So, how these Maxwell's equations can be derived? So, in order to derive Maxwell's equations, let us take three variables x, y, z. If you take z is a function of x comma y, then the differentiation of the z dz can be written as dou z by dou x at y into dx plus dou z by dou y at x into dy. Now, if you take this value as m, what is that value? Dou z by dou x at y as m. And if you write dou z by dou y at x as n, then this equation, this relation can be written as dz equal to, instead of this one, we can substitute m, and we have dx here. Dz equal to m dx. Similarly here, plus, instead of this one, you can write n, and we have dy here and dy. So this equation can be modified into this form. So dz equal to m dx plus n dy. Now, if you take partial differentiation of m and dn, if you take partial differentiation of m with respect to y, similarly, if you take partial differentiation of n with respect to x, you see, what is m here? Dou z by dou x at y. Dou z by dou x at y. Now, if you take partial differentiation of this partial differentiation with respect to x, how it can be written? Dou m by dou y. Instead of m, you can write dou z by dou x at y. So, dou m by dou y at x equal to dou by dou y of, instead of m, you can write dou z by dou x at y, this whole partial differential at x. So, this can be written as, you see, here dou by dou y of dou z by dou x. That is why we can write dou square z by dou x dou y. And we have at y and at x. That is why we can write xy. We can write xy. So, if you take partial differentiation of m with respect to y, then it can be written as dou m by dou y at x equal to dou square z by dou x dou y at xy. Similarly, if you take partial differentiation of n with respect to x, so dou n by dou x, dou n by dou x at y, at y. So what will happen here? Dou by dou x of, what is the value of n? Dou z by dou y, dou z by dou y at x. Here this value, whole at y. So this whole differentiation at y. Now this can be written as dou square z by dou x dou y at x. You see, the partial differentiation of m with respect to y. Similarly, the partial differentiation of n with respect to x are both are equal here. So that is why we can equate these two partial differentiations. So from this, we can write that dou m by dou y at x equal to dou n by dou x at y. So this is the condition can be applicable to any exact differentiation. Now, using these two equations, what are those equations? The first one is, you see here, this is the equation. dz equal to m dx plus n dy. Similarly, this equation, what is this equation? Dou m by dou y at x equal to dou n by dou x at y. So using these two equations, you can derive Maxwell's equations. So by using these Maxwell's equations, you can analyze any sort of condition, or you can derive any sort of equation in the thermodynamics. So remember that these two equations to be applied in order to derive Maxwell's equations. What are those equations? dz equal to m dx plus n dy, and the other one is dou m by dou y at x equal to dou n by dou x at y. Okay. Now let us move to the topic how to derive the Maxwell's equations. Remember that you should remember the two equations. What are those? dz equal to m dx plus n dy. After that, you should remember dou m by dou y at x equal to dou n by dou x at y. So in order to derive the Maxwell's first equation, let us go to the total internal energy relation. What is that relation? So du equal to tds minus pdv. du equal to tds minus pdv. We have already derived this in the previous topic. Let this is equation number 1. Now what you have to do now is, you should compare this equation with the equation dz equal to m dx plus n dy. You should compare each and every variable with the variable of this equation. You see, here in place of z, you have u here. Similarly, in place of m, you have t here. Similarly, in place of x, you have s here. Similarly, in place of n, you have minus p, not p, minus p here. Similarly, in place of y, you have v here. So these to be written like this. So m tends to t, x tends to s, n tends to minus p, and y tends to v. Y tends to v. Now you have to substitute these values in place of these values in the below equation. What is that equation? Dou m by dou y at x equal to dou n by dou x at y. Dou n by dou x at y. Easy. If you substitute m here, what is the value of m here? T. So you see, dou t by, what is the value of y here? V. Dou t by dou v, what is the value of x here? Yes. So dou t by dou v at s equal to, here we have dou n by dou x at y. If you substitute the related values, what is the value of n here? Minus p. So what is the value of x here? Yes. And what is the value of y here? This is v. So minus dou P by dou S at V. Now, this equation is called Maxwell's first equation. So, in order to derive the Maxwell first equation, you should have compared the total internal energy relation with the equation dz equal to mdx plus ndy. Then you have to compare every variable with each other, and you should write these variables in place of mx and y in the equation dou m by dou y at x equal to dou n by dou x at y. Then you can get the first relation of Maxwell's equation. Now let us move to second one. So in order to find out or determine Maxwell's second equation, you should go for enthalpy relation. What is the enthalpy relation? According to Maxwell's potential, Tz equal to Tds plus Pdp. Now you should have compare this equation with the equation with the this procedure you have to follow to in order to determine the other Maxwell's equations. So this equation should be compared with the equation dz equal to mdx plus ndy. If you compare the variables, then you can get m tends to t, x tends to s, n tends to v, and v tends to p. You see, so m tends to t, x tends to s, and n tends to v, and y tends to p. Okay, if you substitute these values, if you substitute these values in place of these values in the below equation, what is that equation? Dou m by dou y at x equal to dou n by dou x at y. So if you substitute these values, you can get the Maxwell's second equation. What is that? Dou t by dou v at s equal to dou v by dou s at t. Okay, now we got the Maxwell's second equation. Now we have to find out the Maxwell's third equation. How we can find out the Maxwell's third equation? For that, we go for Helmholtz relation. Helmholtz thermodynamic function relation. What is that? D phi equal to minus PdV minus ST. Okay, now we have to compare this equation again with the equation. What is that equation? Dz equal to mdx plus ndv. So if you compare these variables again, you can get m tends to minus p, x tends to v, n tends to minus s, and y tends to t. Now if you substitute these variables in the place of mx and y in the below equation, what is that? Dou m by dou y at x equal to dou n by dou x at y. Then you can get Maxwell's third equation. What is that? Dou p by dou t at v equal to dou s by dou v at t. This is called Maxwell's third equation. Okay, now let us move to find out Maxwell's fourth equation. So in order to find out Maxwell's fourth equation, again you go for the relation. What is that relation? Gibbs relation. So the thermodynamic function, potential Gibbs free energy can be defined with the relation dz equal to minus sdt plus pdp. So if you compare this equation again with the equation, what is that equation? Dz equal to mdx plus ndy. Okay, then you can get these variables in place of these variables. If you substitute these values in the below equation, dou m by dou y at x equal to dou n by dou x at y, then you can get the Maxwell's fourth equation. What is that? Minus dou s by dou b at t equal to dou v by dou t at t. Like this, you can derive all the Maxwell's four equations in a very simple manner, in a very easy manner. One can derive Maxwell's four equations. So what you have to do first, you should have take two equations. What is that? Dz equal to mdx plus ndy, and after that you should have take dou m by dou y at x equal to dou n by dou x at y. So every thermodynamic potential equation should be compared with this equation. After comparing with this equation, the variables should be replaced with these variables in the below equation. Then you can get the Maxwell's equation. So from thermodynamic potential, that is internal energy relation, you can get Maxwell's first equation. From the relation of enthalpy, you can get Maxwell's second equation. From the relation of Helmholtz free energy, you can get Maxwell's third equation. From the relation of Gibbs function, you can get Maxwell's fourth equation. Okay, so but you see, the Maxwell's equations are very difficult to remember. It is very, very difficult to remember at a stretch. So there is an idea to remember these four Maxwell's equations. సో మనకు ఒక చిన్న చిట్కాని ఉపయోగించి చాలా చక్కగా ఈ 4 Maxwell's equations should be remembered by using this technique, a small technique. So what is the technique? For that, you see, let us draw a rectangle like this. So after that, you should have draw the two diagonals like this. So you should name every edge like this: P, S, T, V. Otherwise, you should remember that we have two diagrams, two graphs in the first chapter: PV diagram and TS diagram. You should remember that. So you should have named the diagonals as PV diagram and TS diagram. Now you can easily remember that technique. So this diagram should be named as PV diagram, and this diagonal should be named as PV, and this diagonal should be named as TS. You have PV diagram and TS diagram in the previous chapter. Okay, now every side should be given a number. This is 1, and this opposite side should be given the number 4. This is number 1 and this is number 4, and this side should be given number 2, and after that the opposite side should be written as number 3. So 1, 4, 2, 3. After that, you see, this equation number 1 should be signed with negative sign, and this number 4 should be shown with the negative sign. So the number 1 and number 4 should be shown with the negative signs. So 1 is minus, similarly 4 is also minus. Okay, after that, you see, here you should draw the arrow marks. At S, you should draw arrow marks like this, and here at T, you should draw arrow marks like this. So this is the figure you should draw to write or remember the Maxwell's equations very easily. So మనం ఒక దీర్ఘచతురస్రాకార బొమ్మను తీసుకుందాం. దీని యొక్క డయాగనల్స్ కి మనము PVTS పటాల ద్వారా గుర్తుపెట్టుకుని మనం వాటికి లెటర్స్ తోటి గుర్తించడం జరుగుతుంది. ఆఫ్టర్ దట్, every side should be given a number 1, 4, 2 and 3, and 1, 4 numbers should be shown with the negative signs. After that, the arrow marks should be directed like this at S and at T. After that, we can write very easily every Maxwell equation. You see, for number 1 in order to write the number 1 Maxwell equation, go for number 1 side. Here we have number 1 side. So now I can explain how to write the Maxwell's equations by using this figure. You see, dou T by dou V. You see, dou T by dou V. What is the diagonal letter to T? Yes. So dou T by dou V at S equal to, you write exactly same direction with the number 4 side. So don't use this arrow mark. Now you are using this direction only. So again, you have to use this direction only, not this direction. So here at number 1 side, You have written dou T by dou V. What is the diagonal letter here? Yes. Dou T by dou V at S equal to, you see, dou P by dou S, dou P by dou S. What is the diagonal letter of P? V. Dou P by dou S at V. So, as the number one is shown with the negative sign, you should have put the negative sign either in this place or in this place. Okay, you don't put the minus on either side of the equation. You should put on just one side of the equation. So, this is equation number one. So, if you, now we can see dou T by dou V at S equal to minus dou P by dou S at V. Now, you go for the equals first equation, either it is correct or not. You see, dou T by dou V at S equal to minus dou P by dou S at V. So, easily one can remember the Maxwell's equations very easily by this technique. Now, we can write the Maxwell's second equation very easily. You see, so in order to write the Maxwell's second equation, you go the number two side. Here, arrow mark is in this direction. So, dou T by dou P. Dou T by dou P. What is the diagonal letter of T? Yes. Dou T by dou P at S equal to exactly. Now, what is the other side of number 2? 3. You have to follow this direction only on the 3 number side also. Dou V by dou S. What is the diagonal letter of V? P. Dou V by dou S at P. Dou V by dou S at P. So, this is equation number 2. That is Maxwell's second equation. Similarly, now you can write Maxwell's third equation also. Now, let us move to number 3 side. What is the arrow mark direction here? Here we have the arrow mark direction. So, you should start with the direction as we shown here. Dou S by dou V. Dou S by dou V at T. What is the diagonal letter of S? T. Dou S by dou V at T equal to, now move on to exact opposite side. So, dou P by dou T at V. Dou P by dou T at V. You see, dou S by dou V at T equal to dou P by dou T at V. Dou P by dou T at V. So, this is the Maxwell's third equation. Okay. Similarly, what is the Maxwell's fourth equation? You see, let us move to the number 4 side. Here we have the arrow mark direction in this way. So let us move from. Let us start from this letter. Dou S by dou P at T equal to. Similarly, in the opposite direction, dou V by dou T at P. So, as the number 4 is given the negative sign, you should have maintain the negative sign either on the left hand side or in the right hand side. So, you see, this is the fourth equation. Dou S by dou P at T equal to minus dou V by dou T P. In this manner, one can remember Maxwell's equations very easily by using this technique. So, like this, the Maxwell's equations are derived by using the Maxwell's potential relations. By using the Maxwell's potential internal energy relation, you can get the Maxwell's first equation. By using the thermodynamic potential enthalpy relation, you can get Maxwell's second equation. By using the thermodynamic potentials potential Helmholtz free energy relation, you can get Maxwell's third equation. By using the Gibbs function relation, you can get the Maxwell's fourth equation. So, how one can find out or one can derive the equations we have seen very clearly. So, in order to remember the Maxwell's 4 equations, once again we have seen a useful a small technique how to remember Maxwell's four equations. So by using all these four equations, one can derive or analyze every concept in the thermodynamics. That is the advantage of Maxwell's equations. Okay,